The statement for Cayley-Hamilton theorem is every square matrix A will satisfy its characteristics equation if the given equation is equal to 0. A square minus 4A plus 3A is equal to a null matrix, then we can say Cayley-Hamilton theorem is verified. The characteristics equation is A minus lambda is equal to 0, that is 1 minus lambda minus 2, 3, 4 minus lambda. If we simplify, we'll get lambda square minus 5 lambda plus 10 is equal to 0. Hello dear students, welcome to this session of Mathematical Foundation class. I am Mr. Niranjan, Faculty, Department of Computer Science, Vidhyaashram First Grade College, the Temple of Excellence. Today in this session, I am going to take very important concept that is regarding Cayley-Hamilton theorem. In the previous class, we have discussed regarding characteristics equation and the characteristics roots, that is eigenvalues. Now, based on that, today I am going to discuss regarding very important concept, Cayley-Hamilton theorem for a square matrix. What is the statement? So, the statement for Cayley-Hamilton theorem is every square matrix A will satisfy its characteristics equation. That is, every square matrix satisfies its characteristics equation is called the Cayley-Hamilton theorem. Very important statement. They may ask for 2 marks. Define Cayley-Hamilton theorems. The answer is every square matrix satisfies its characteristics equation. Suppose if A is a square matrix of any order, 2 rows 2 column or 3 rows 3 column. If A is a square matrix of order n into n, then the characteristics equation of the matrix A is nothing but A minus lambda I. So the characteristics equation is determinant of A minus lambda is equal to 0. So if you simplify this, you will get a quadratic equation or a cubic equation depending upon the order of the matrix. Now, if it is second order, you will get a quadratic equation. If it is a 3 rows 3 column, you will get either quadratic equation or a cubic equation. So, what is the statement for Cayley-Hamilton theorem is every square matrix satisfies characteristics equation, that is A minus lambda is equal to 0 determinant is the characteristics equation of a square matrix. Now, let us move on to the first problem. Take an example. Verify Cayley-Hamilton theorem for the square matrix 2, 1, 1, 2. So, let us consider, let the given matrix is, let matrix A is equal to 2, 1, 1, 2. The characteristics equation, you know the characteristics equation. The characteristics equation is A minus lambda I. So, A minus lambda is equal to 0. Determinant A minus lambda is equal to 0. First find out A minus lambda I. A minus lambda I is equal to, what is matrix A? 2, 1, 1, 2 minus lambda into 1, 0, 0, 1. This is equal to 2, 1, 1, 2 as it is minus lambda 0, 0, lambda. So, this can be written as 2 minus lambda, 1 minus 0 is 1, again 1 minus 0 is 1, again 2 minus lambda. Right, see here 2, 1, 1, 2 minus lambda 0, 0, lambda. Subtract this 2 minus lambda, 1 minus 0 is 1, 1 minus 0 is 1, again 2 minus lambda. Now, the characteristics equation A minus lambda determinant is equal to 0. So, determinant of A minus lambda I is 2 minus lambda 1, again 1, 2 minus lambda is equal to 0. Simplify this. 2 minus lambda into 2 minus lambda is 2 minus lambda whole the square minus 1 is equal to 0. Now, this is of the form A minus B whole square. A minus B whole square. A square 2 square is 4 plus B square lambda square minus 2AB 2 2 is 4 lambda minus 1 is equal to 0. Now, put it in order. Lambda square minus 4 lambda. 4 minus 1 is plus 3 is equal to 0. This is the characteristics equation. Let us represent this as equation number 1. So, if you solve this, you will get the eigenvalues, right? Now, the concept here is to verify the Cayley-Hamilton theorem. So, to verify Cayley-Hamilton theorem, put lambda is equal to A and multiply by an identity matrix. That's it. Now, to verify Cayley-Hamilton theorem, CS theorem, put lambda is equal to A and multiply by an identity matrix of same order. So to verify Cayley-Hamilton theorem, put lambda is equal to A and multiply by the identity matrix of same order. Now put lambda is equal to A and multiply by an identity matrix. So what you will get? A square minus 4A plus 3I is equal to 0. Now to prove that A square minus 4A plus 3I is equal to 0. Now just find out A square. What is A square? A into A, matrix A into A. A is nothing but given matrix 2, 1, 1, 2, again 2, 1, 1, 2. Simplify this. So 2 2s are 4, again 2 into first row, first column, 2 2s are 4, 1 1s are 1, again 2 1s are 2 plus 1 2s are 2. Again second row, first column, 1 2s are 2 plus 2 1s are 2. Again 1 into 1 is 1 plus 2 2s are 4. That's equal to 5, 4, 4, 5. Now take LHS. What is LHS? A square minus 4A plus 3I. This is equal to, what is A square? 5, 4, 4, 5 minus 4 times matrix A, 2, 1, 1, 2 plus 3 into identity matrix 1, 0, 0, 1. So that's equal to 5, 4, 4, 5 multiply by 4, 4 2s are 8, 4 1s are 4, 4 1s are 4, 4 2s are 8 plus multiply by 3, 3, 0, 0, 3. What is this equal to? If we simplify this, see 5, yes, 5 minus 8 is minus 3 plus 3 gets cancelled 0, 4 minus 4 is 0 again, 4 minus 4 is 0 again, 5 minus 8 plus 3 is equal to 0, that is equal to, that means A square minus 4A plus 3I is equal to 0. Therefore, Cayley-Hamilton theorem is verified. CH theorem is verified. That's it. So the Cayley-Hamilton theorem is verified. Just find out the characteristics equation and to verify Cayley-Hamilton theorem, just put lambda is equal to A and multiply by an identity matrix of same order if the given equation is equal to 0. A square minus 4A plus 3I is equal to a null matrix, then we can say Cayley-Hamilton theorem is verified. That's it. Very important problem for the point of examination. Now let me take one more problem. Verify Cayley-Hamilton theorem for the square matrix 1, minus 2, 3, 4 and hence find the inverse of the matrix. Now let us write, let A is equal to given matrix. What is A? 1, minus 2, 3 and 4. Now the characteristics equation is determinant A minus lambda is equal to 0. Now first find out A minus lambda I. A minus lambda I is equal to, what is matrix A? 1, minus 2, 3, 4 minus lambda into 1, 0, 0, 1. That's equal to 1, minus 2, 3, 4 multiply by lambda. Lambda into 1 is lambda, 0, 0, lambda. Subtract this. Now therefore, A minus lambda is equal to 1 minus lambda, minus 2 minus 0 is minus 2, 3 minus 0 is 3, 4 minus lambda you will get. Right. Now we know what is the characteristics equation. Now determinant A minus lambda is equal to 0. That is determinant 1 minus lambda 3, then minus 2, 4 minus lambda is equal to 0. Simplify this. What we will get? 1 minus lambda into 4 minus lambda, minus into minus plus, 3 2s are 6, 1 into 4 is 4, 1 into lambda is lambda, minus 4 lambda, minus into minus plus lambda square plus 6 is equal to 0. Put it in order. Lambda square minus 4 minus 1 is minus 5 lambda, 6 plus 4 is 10 is equal to 0. Let us represent this as equation number 1. Right. This is the common step. So the characteristics equation is A minus lambda is equal to 0. That is 1 minus lambda minus 2, 3, 4 minus lambda. If we simplify, you will get lambda square minus 5 lambda plus 10 is equal to 0. To verify Cayley-Hamilton theorem, put lambda is equal to A and multiply by an identity matrix of same order. So that is lambda is equal to a square minus 5a plus 10I is equal to 0. Now to verify this, just find out the value of a square. Now what is a square? A square is equal to a into a. What is a? A is 1 minus 2, 3, 4. 1 minus 2, 3, 4. Again 1 minus 2, 3, 4. Simplify this. So this is equal to 1 1s are 1, minus 2 3s are 6, 1 2s are 2, minus 2 4s are 8. Again, second row, first column, 1 3s are 3, plus 3 4s are 12, 3 2s are 6, minus 6 plus 4 4s are 16. This is equal to minus 5, minus 10, that is 15, and minus 6 plus 16 is plus 10. Right. Now let us take LHS. Now LHS, what is LHS? A square minus 5a plus 10I. So if this is equal to a null matrix, then Cayley-Hamilton theorem is verified. What is a square? Minus 5, minus 10, 15 and 10 minus 5 times a. 1 minus 2, 3, 4 plus 10I means 10, 0, 0, 10 straight away you can put. So this is equal to minus 5, minus 10, 15 and 10 multiply by 5. 5 1s are 5 2s are 10, 5 3s are 15, 5 4s are 20 plus 10, 0, 0, 10. What is this equal to? Minus 5 is minus 10, minus 10 plus 10 is 0, 15 minus 15 0, 10 minus 20 is minus 10 plus 10, 0, 0, 10. What is this equal to? Minus 10 plus 10 is 0, 0 plus 0 is 0, 0 minus 10 plus 10, that's equal to 0. A null matrix. That means, so a square minus 5a plus lambda 10I is equal to 0, a null matrix. Therefore, Cayley-Hamilton theorem is verified. So we can say that, therefore, Cayley-Hamilton theorem is verified. Right here, therefore, Cayley-Hamilton theorem is verified. That is, CH theorem is verified. Cayley-Hamilton theorem is verified. Now, what is the problem? Verify Cayley-Hamilton theorem and hence find the inverse using that. Right. So, to find inverse, next, to find A inverse. Now, from this, from 1, what is the equation 1? We have this A square, or call it as equation number 2. From 2, A square minus 5a plus 10I is equal to 0. From this, find out the inverse. Very simple. Just multiply by A inverse on both sides. This is A square into A inverse minus 5a A inverse plus 10I A inverse is equal to 0. This A square can be written as A into A inverse. A into A is A square minus 5 times A inverse plus 10I A inverse. So, you might have been studied while solving the problems in matrices and determinants. Any matrix into identity matrix or identity matrix into any matrix is equal to the same matrix. I into A or A into I is equal to A. Similarly, a matrix into inverse or inverse into the same matrix is also equal to an identity matrix. These are the two important properties. So, A into A inverse is equal to an identity matrix. Again, 5A inverse is equal to an identity matrix plus 10 into any matrix inverse into an identity matrix is equal to inverse, A inverse. So, A into I is equal to A minus 5I plus 10A inverse is equal to 0. Now, just what is required to find is inverse. Keep 10A inverse and transfer plus 5I becomes minus 5I and plus A becomes minus A. Now, substitute here. That's it. Okay. To find the inverse, just multiply both sides by A inverse. A square into A inverse minus 5A inverse plus 10I A inverse. A square can be written as A into A inverse, so A inverse is equal to I into A inverse is equal to again A inverse, A into I is equal to A minus 5i plus 10A inverse is equal to 0, or 10A inverse is equal to transfer minus 5i becomes plus 5 and A plus A becomes minus A. Now therefore 10 times A inverse is equal to 5 into identity matrix means 1 0 0 1 minus, substitute the value of A. What is the matrix A? A is equal to 1 minus 2 3 4. 1 minus 2 3 4. Simplify this. So 10 times A inverse is equal to 5 0 0 5 minus 1 minus 2 3 4. So 10 A inverse is equal to 5 minus 1 is 4, 0 minus into minus is plus 2, 0 minus 3 is minus 3, 5 minus 4 is 1. So therefore the inverse A inverse is equal to 1 over 10 into 4 minus 3, 2 and 1. That's it. This is the inverse using Cayley-Hamilton theorem. Very important problem. You may expect this type of question for 8 marks or 7 marks. Right. Now let us move on to the next third problem. If A is equal to 2 minus 1 0 1, verify Cayley-Hamilton theorem for the square matrix and find the inverse of this matrix. Similar problem as that of the second one. Now what is given? Let A is equal to, the matrix A is equal to 2 minus 1 0 1. Write down the characteristics equation. The characteristics equation is A minus lambda I is equal to 0 under determinant. That is determinant of A minus lambda is equal to 0. Now first find out A minus lambda I. What is A? A is equal to given matrix 2 minus 1 0 1 minus lambda into 1 0 0 1. That's equal to 2 minus 1 0 1 minus lambda 0 0 lambda. This is equal to 2 minus lambda. Minus 1 minus 0 is minus 1, 0 minus 0 is 0, 1 minus lambda. Right. Now the characteristics equation A minus lambda is equal to 0 means 2 minus lambda minus 1 0 1 minus lambda is equal to 0. Simplify this. So what you will get? 2 minus lambda into 1 minus lambda, minus into minus plus 1 into 0 is 0 is equal to 0. If we simplify this, 2 into 1 is 2, minus 2 into lambda is 2 lambda, minus lambda, minus into minus plus lambda square is equal to 0, or put it in order, lambda square minus 3 lambda plus 2 is equal to 0. Lambda square minus 3 lambda plus 2 is equal to 0. Okay, see here, 2 minus lambda into 1 minus lambda, minus 0 into 1 is 0 is equal to 0. 2 into 1 is 2, 2 into lambda, lambda, 2 lambda, 1 into lambda is lambda, minus into minus plus lambda square minus 3 lambda plus 2 is equal to 0. Now lambda square minus 3 lambda plus 2 is equal to 0. Let us represent this as equation number 1. Now, to verify, this is the characteristics equation. To verify Cayley-Hamilton theorem, the Cayley-Hamilton theorem can be verified by put lambda is equal to A and multiply by an identity matrix of same order in equation number 1. So then what we will get? A square minus 3A plus 2I is equal to 0. Now verify A square minus 3A plus 2I is equal to 0 in null matrix or not. Now just find out A square. What is A square? A into A. What is A? A is given matrix 2 minus 1 0 1. Again A 2 minus 1 0 1. Now multiply first row, first column, second column. That's equal to 2 2s are 4. 2 into 2 4, minus 1 into 0 is 0. Again 2 1s are 2, minus 2 minus 1. Second row, first column, second column, 0 into 2 is 0, 1 into 0 is again 0. 1 into 0 is 0 plus 1 into 1 is 1. That's equal to 4 minus 3, 0 and plus 1. Now substitute here. Now a square minus 3a plus 2i. Verify this is a null matrix or not. This is equal to a square 4 minus 3 0 1 minus 3 into a is equal to 2 minus 1 0 1 plus 2 times identity matrix means 2 0 0 2. So this is 4 minus 3 0 1 multiply by 3 3 2s are 6 3 1s are 3 0 3 1s are 3 plus this is 2 0 0 2. What is this equal to? So 4 minus 6 is minus 2, minus 3 plus 3 gets cancelled 0, 0 minus 0 is 0, 1 minus 3 is minus 2, 2 0 0 2. What is this equal to? 0 0 0 0 is equal to 0, a null matrix. Hence Cayley-Hamilton theorem is verified. Therefore, conclude it, Cayley-Hamilton theorem is verified. This is how we are going to verify Cayley-Hamilton theorem. Now, the next part of this problem is to find the inverse. To find A inverse, what we have? A square minus 3a, a square minus 3a plus 2i is equal to 0 from equation number 2. Call it as equation number 2. From 2 we have a square minus 3a plus 2i is equal to 0. Multiply by A inverse on both sides. What you will get? A square into A inverse minus 3a A inverse plus 2i A inverse is equal to 0. A square can be written as A into A. A inverse minus 3a A inverse plus 2 times I into A inverse. So this is A into, you know, A inverse is I, A inverse is I, plus 2 into I into A inverse is equal to A inverse. A into I is equal to A minus 3I plus 2A inverse is equal to 0. Now what is to find is A inverse. 2A inverse is equal to minus 3I becomes plus 3I and plus A becomes minus A. Now simplify this. Now 2A inverse is equal to 3i minus a. 3 into identity is 1 0 0 1 minus a is nothing but the given matrix 2 minus 1 0 1, 2 minus 1 0 1. Now multiply it, 3 0 0 3 minus 2 minus 1 0 1. Simplify this. 2 times A inverse is equal to 3 minus 2 is 1, 0 minus into minus is plus 1, then 0 minus 3 is 0, 3 minus 1 is 2. This is the inverse. See the elements we have, yes, if interchange 1, 2 minus, yes, correct. So therefore, A inverse is equal to 1 over 2 into 1 1 0 2, that's all. This is the inverse for the given matrix. If you want straight away, you can verify using this matrix. What is A? A is equal to 2, 1, 2 minus 1, 0. Interchanging the diagonals, 2, 1 can be plus 1, 2, and changing the signs means minus 1 becomes plus 1 and 0. So, hence the A inverse A inverse is equal to 1 over 2 into matrix 1, 1, 0, 1 is the inverse for the given matrix. This is how we are going to find the inverse. So, this is very important concept. So, definitely a sure question, you will expect one question from this. Verify Cayley-Hamilton theorem and hence find the inverse using Cayley-Hamilton theorem. So, inverse can be obtained through this Cayley-Hamilton theorem, the characteristics equation only, right? Not by general method. That's all regarding today's session. Let us meet with the different concept in the next session. Thank you very much.